So I want to show you now how to find the equation of a tangent line if you have a vector-valued function. So remember, a vector-valued function, we're going to have some function, usually r of t, and it's going to have an x of t, y of t, and z of t component. So they're each defined independently. So for a tangent line, right, we always need, right, a slope and a point. So let's think about how we might find those when we're talking about a vector-valued function. Now, I started off with a 2D curve over here just so that I had some hope of graphing it. So we're going to let C be this curve that's traced by our vector-valued function, r of t. And I'm going to start at this point, t naught. So some place where we start, we could have a vector r, right, of t naught that goes, right, the position vector from the origin out to that point on our curve. And then, right, sometime later, right, we've swooped around and we've gotten to a new point, t naught plus some, right, delta t, some increment of time. So the difference between those, right, that vector that goes between them, right, is going to be, right, the difference between those two vectors. So this here is r at t naught plus delta t. Okay. So as you can imagine, if you think back as to how, when you first started talking about derivatives, if we swoop this r at t plus delta t, if, right, delta t gets smaller and smaller, so as that point, right, comes in closer and closer to t naught, the slope of this difference is going to become, right, the slope of the tangent. So what that's going to look like, right, is we want to take r at t naught plus delta t minus, right, r at t naught, and then, right, divided by delta t. And as we take the limit, as delta t gets really small, right, as we swing this second vector in closer to the first one, what we get, right, is the derivative. So r prime at t naught. Right? And remember, r prime, if this is our r vector, r prime is just, right, differentiate component-wise. So x prime of t, y prime of t, and z prime of t. Now, the other thing we need to know is remembering how we parameterize a line. Okay. Oh, and I guess I've gone to 3 space already. So this is what it'll look like there. If we're in 2 space, we just leave off our z. So to find the equation of the line, so this is going to be our slope, right? And then we also need a point. So the point, right, that is we know for sure is on our curve is the point at the end of this r at t naught. So r of t naught, so our point is r at t naught, okay? And our slope, the direction vector here, is r prime at t naught, okay? And then the equation of the tangent line, parametrically, so if we use L of t, is going to be equal to, right, our starting point, so r of t naught, plus, so now we're going to have this parameter t, and then times r prime at t naught. Get all my vectors on top there. Okay. So this t, what it's going to do is it's just going to let us get all of the points that are tangent. So I'm going to go ahead and just kind of guesstimate where that might be up here. So I'm going to draw this is my tangent line, vectorly, right? So I've got the direction from the derivative. I've got my anchor point from the original vector function. And then this parameter t is just going to let us get all of the points along that vector. Okay, so let's go ahead and practice. I've got r is equal to 2 cos t, 4 sine t. It's this ellipse down here in 2 space that I've got drawn. You can convince yourself it starts here at t equals 0. Retrace out this way. Okay. So let's find the parameterization of the tangent line at t equals 4 pi thirds. And notice I say find a parameterization, right? Parameterizations are not unique. You can always, right, change your parameterization if you need to get someplace faster or slower, right? Whatever that's going to be. All right, so I need r at 4 pi thirds. So what's that going to be? All right, well, I don't know, 2 cosine 4 pi thirds, 4 sine 4 pi thirds, right? You're going to grab your calculator. You're going to draw a quick little unit circle like I do. So 4 pi thirds is over here. So it looks like they're both going to be negative. Cosine is the negative 1/2. So I have 2 times negative 1/2. And so then the sine is going to be negative root 3 over 2. So if I just tidy that up, so my point, my anchor point, is negative 1 and then negative 2 root 3. Cool. And then the slope, so now I need r prime of t. So just finding our derivative, so that'll be negative 2 sine t and then 4 cosine t. So just doing first derivatives. And then let's find that at 4 pi thirds. Okay, so sine of 4 pi thirds, and again, that's our negative root 3 over 2, so times negative 2. Negative 2 times root 3 over 2, I'll write it out, and then I've got 4 times negative 1/2. So tidying that up, it looks like we've got negative root 3 and then negative 2. Okay. So putting that all together into the equation of our tangent line, right, so it's our point, negative 1, thank you, negative 2 root 3 plus t times the slope, negative root 3, negative 2. Let's see if that makes sense. So here's our picture. So 4 pi thirds, right, over here in quadrant 3. So 4 pi thirds, right, the point is negative 1, negative 2 root 3, right, so I'm down here. Here's my point. And so we're talking about, right, the vector, here's that r naught. Okay. Negative 1, negative 2 root 3. So then the slope of the tangent there, so I like that this is negative, but I kind of wish my r prime, my x version, was positive, right? So if I go in and I draw the tangent line there, what it looks like it is, right? It's definitely going in a negative y direction, but the x direction, right, it's going in the positive x direction. So I'm going to go check my signs real quick. So I have r prime, so here's my r, so its derivative is going to be negative 2 sine t, that's good. The derivative of sine is 4 cos t. That's good. Okay, so now we're going to evaluate it at 4 pi thirds. So the sine of 4 pi thirds is, sine of 4 pi thirds, oh, there it is negative root 3 over 2, right? So I have a negative times a negative, so that's going to make that a positive square root 3. Okay, so that's going to change this down here to a positive square root 3, which is good, right? So I'm glad I checked because I found that sign mistake that I made. Okay, so here's the equation of that tangent line, right? And you could plug in different values of t to come up with different points along that tangent line. Okay, let's do one more, and let's do it in 3D. I will not try to graph it, but I might try to pull up, I have it graphed on the computer, so I might let you see that if I can figure out how to do it. Okay, so Find the parameterization of a tangent line at pi fourths. So I've got r. Let's go ahead and find r prime. I'm going to go ahead and switch to blue. That's not showing up very well, is it? So r prime. So the derivative of cosine is negative sine t. Derivative of sine t is cosine t. The derivative of 3 cosine squared t, so be careful. So the 2 comes down, so I'll get 6 cosine t times the derivative of what's inside, which is going to make what's inside, right, was cosine. So that'll be a negative sign. So I'm going to put the negative out front. Sine t. Then we'll evaluate both of those at our particular t value. So r at pi fourths. So I've got the cosine of pi fourths, the sine of pi fourths, and 3 times the cosine of pi fourths, quantity squared. Go ahead and do those calculations. So 1 over root 2. I'm not a rationalizer. 1 over root 2. So 1 over root 2 squared is going to be 1/2 times 3 is going to be 3/2. Okay, there's our point. And then our slope, so r prime at pi fourths, what do we got? So I've got negative sine of pi fourths, cosine of pi fourths, and then negative 6 cosine pi fourths times the sine of pi fourths. So I get negative 1 over root 2, 1 over root 2. And let's see, 1 over root 2 times 1 over root 2. So there's a 1/2 again times negative 6. That'll make that negative 3. So there is my direction vector. Oh, I left off my vectors. Okay, so putting it all together for the equation of our tangent line at pi fourths, right? It would be different if we were at a different time. So we get r. So our particular point that we know is on the curve plus t times the direction vector, t times that slope. So you could write these, right? You could write these component-wise, right? So your x of t, right, 1 over root 2 minus 1 over root 2t. Y of t is its, right, starting value, 1 over root 2, plus 1 over root 2t. And then the z component, starting at 3/2, minus 3t. Okay, I'm going to pause and see if I can bring up that graph of this particular equation. So you can see I have that point plotted right there. I'm going to swoop around so you can kind of see it. So there's that point where we're tangent, right? So 1 over root 2, 1 over root 2, 3/2. So the line tangent at that point, right, it's going to be going in the positive x direction. I'm sorry, negative x direction, positive z direction. Positive y, negative z, and negative x.